Okay, so um, now to be as general as possible, now that we have this arbitrary function in x, okay, this is again a wave function, or you can write an arbitrary wave function that's a superposition state, and that wave function actually has a time dependence as well that we've neglected so far. So we have to remember that each eigenfunction, there should be an n here. Each eigenfunction, okay, which we've been talking about, the eigenstates psi sub n's, have a time dependence as well, and that gives you the total wave function that in this case is depends on x and t, the position and the time. Okay, so we write out explicitly the expression for the spatial eigenfunctions, and then we have the expression for the time dependence here. Remember, En is just as we gave on the first view graph. So so the most general solution then of the Schrodinger equation, that is for an arbitrary state, is where we'll call that arbitrary state now, which is a function of position and time, capital psi, and that's equal to the sum from n equals 1 to infinity of these amplitude coefficients times the spatial eigenfunctions times the time dependence that's associated with each one of those eigenfunctions. And again, now you see the n dependence throughout here. And again, to find now for this arbitrary excuse me, for this arbitrary solution to the Schrodinger equation, okay, the superposition state, okay, superposition, in order to find, in the most general way, in order to find these coefficients, you project the wave function at a particular time, t equals 0, okay, onto the basis state. I mean, onto the basis function, the eigenfunction psi sub n, the complex conjugate of that. You multiply those two, and that gives you do the integral, and that gives you the amplitude coefficients. Okay, and so when time equals 0 here, then the time dependence, this term just becomes 1. Okay, and so it's basically back to what we had done before. Okay, so the time dependence for these stationary states, the time dependence essentially when you're finding these amplitude coefficients kind of goes away. Okay. Alright, so now let's get back. So since the time dependence goes away, let's just again look back at the spatial dependence. So let's just consider the spatial part of the wave functions. So if we have an arbitrary function f of x, okay, that's normalized, what that means is that if we multiply the function by its complex conjugate and we integrate over all space, that we'll get unit. That means that again that tells you that this wave function f of x, this arbitrary function, superposition state, describes the state of a single particle, and we know that particle has to be somewhere. This is the probability density, if you remember, psi star psi, and so that has to be, the particle has to be somewhere. So if we integrate the probability density over all space, we have to get 1. And then again, these Cn coefficients are just a projection of this function onto the basis states. And this normalization condition here, basically implies that the sum of the square of these the squared magnitude of these amplitude coefficients has to be equal to 1. Okay, and again, those of you who may have seen this in another context, in a math class, this basically relationship between the sum of the coefficients squared and the normalization is Parseval's theorem for a Fourier series.